Welcome to your lesson on power models. In this lesson, we'll look at specifically quadratic versus cubic. So until now in our unit on power models, we've been focused on quadratic models. However, there are many other types of power models. Quadratics are just one type where the power is a square. What if we have equations where the power is a 3? These are called cubic functions. What if it was a power of 4? So anyway, power functions can go to infinity because the power can become any number. But we'll focus on quadratic versus cubic, which means power 3. Let's begin here. So quadratic functions look like this. This is the general or standard form we looked at. Ax squared plus bx plus c. Of course, we looked at factored or intercept form as well, but this is the general form. Now, cubic functions look like this. So same format, but notice now our first power is a cube. That's why they're called cubic functions. And then we have bx squared plus cx plus d. So they're the same order where we have the decreasing values of the exponent. Of course, sometimes some of these parameters have a value of 0, so you won't see x squared or you won't see x or whatever, but in general they look like this. So let's investigate the difference between quadratic and cubic functions on Desmos. Let me take you there now. So we're going to look at it here. Here, first of all, we have a quadratic. See, there's our general form of quadratic. I've graphed it here. I'm going to change the parameters and we're going to talk about some things. But in general, we know a quadratic has this kind of shape. It can be like this, or if a was positive, it can open like that. So concave up or concave down. In general, a quadratic will always have a minimum or a maximum point. That point is the vertex, right? The upper point or the lower point, depending on whether it's opening up or down. So max or min. Every quadratic will have a max or min. A lot of quadratics will also have two x-intercepts, right, where it crosses the x-axis here. So we see two x-intercepts. However, if this one opened up like this, it has no x-intercepts. I could slide the whole parabola down, however, by changing the c value there, and now it does have two x-intercepts. So the point with parabolas are they will have two x-intercepts, or if I slide it up a little bit, they will only have one x-intercept if the vertex sits right on the axis, or they will have no x-intercepts if it sits above, right? So no x-intercepts, one x-intercept, and two x-intercepts. So those are parabolas. They have a max or min, they have x-intercepts, and that's it. Let's take a look now at a cubic compared to that. So here's a cubic. So there we saw our quadratic, and now we see a cubic together with it. Look at the differences and the similarities here. Okay, notice the parabola had that one change in direction where the vertex is. Notice a cubic has two changes of direction. So it has like two max min points, right? Like quadratic had one, now it has two. One, two. So it's kind of like two parabolas together in a way. But not all cubics will have those max or min. Like every parabola must have a max or min point, the vertex, but not all cubics will. So let me show you a few things about cubics. Okay. So there's your parabola, your cubic. All right, I'm going to move the cubic up and down. Okay, so let me close the parabola so we can just see the cubic now. All right, so changing the a value of the cubic. I'm going to change the a. Look, it's becoming like that. You can see a max point, a min point. Change it some more. Change it so you can still see max or min. But if you go a little further, let me show you as I change the b value and c as well. Look at that. All of a sudden, look, now the cubic has a max or min, but when I change the c value, look what happens. It no longer has a max or min. It seems to travel in one direction. It has a big slope, less, and then big slope again. So it doesn't have those max or min points again. That's important to know about cubics. All parabolas will have a max or min, but all cubics will not. See, some cubics will have a max or min like this, but some will not. They'll look like this. All right, so now let's talk about intercepts. I see one intercept. When it has no max or min, when it flows one way, it only has one x-intercept. But when I have multiple max or min, so let's change that again, like this, and now I move it up or down, I can see one x-intercept, or if I move the whole thing down, now I see 1, 2, 3 x-intercepts, right? So a cubic can have 1, 2, 3 x-intercepts, or just one x-intercept, or it can also have two. How would two be possible? Think about that. How would two be possible? Well, let me see. Let me drag it right to the axis. I can't get it perfectly there, but imagine this just like a parabola. When it hits, the vertex here hits right on the axis, that would be one x-intercept and another one here. So two x-intercepts or three x-intercepts like this, 1, 2, 3, or no, or only one x-intercept if I move this like that or like that. So important things to know about cubics. Hope that exploration that you see the things a little bit. Let's continue. So cubic functions look like this. And here are the notes of what we just saw in our exploration. Not all cubic functions have a maximum minimum turning point, right? Some have the max and min, and some don't have it at all. Some have neither, it says. Also, cubic functions can have 1, 2, or 3 roots, and the roots again are the x-intercepts, and we saw that in our investigation there. These are key points. Make sure you know that about cubics. Okay, so here's an example of a cubic that has only one intercept and no max or min, right? It flows like that. There's no max or min. Here's an example of a cubic that has one intercept still, but it has a max or a min. And then here's an example of a cubic that has max or min and 3 intercepts, 1, 2, 3. And the only situation we're missing here again is the one with 2 intercepts, which could be considering if you took this one, imagine this whole one sliding down until this point right here sat right on the axis. Then there will be 1, 2 x-intercepts. So remember those key points and pause here if you need to, just to soak that idea in. Okay, so now we're going to talk about sketching graphs. We've already sketched graphs of quadratics. Now we're going to look at sketching graphs of cubics using our calculator. So to sketch, when you're asked to sketch in the IB world, it means draw a pretty detailed sketch, not super detailed, but detailed enough that you have some key points labeled and so on, and that they're accurate. So let's try to sketch this one. Punch this one in your calculator and let's see what it looks like when we graph that. So I'm going to get my calculator here. I'm going to enter it also. So enter y equals, enter that equation, parenthesis x minus 2, end parenthesis power 3. We have a cubic. I'm going to hit zoom, and number 6, remember zoom 6 is zoom standard, which means it makes a standard graphing window 10, 10, 10 in every direction. I can see the cubic pretty clearly. I might not need to see all these negative values, so I'm going to change the window and do x min at 0. Or maybe let's make it -1. X min at -1. Graph it again. Okay, yeah, I can pretty clearly see my graph. Now you may remember to find things like x-intercepts and y-intercepts, we can use calc. So second calc, if I want to know, for example, what the 0 is. 0 means the x-intercept. So I'm going to go to there, press that. Left bound means you go to the left of your x-intercept, which I think I already am, I'm guessing. I don't know where we are. Oh, I'm way beyond. Okay, let me... There it is, here it comes. Okay, there's the cursor on my curve. I'm going to go beyond the x-intercept there. So left of the x-intercept, then right of the x-intercept. I'm going to go to the right of it, like that. Enter, and then guess, remember, means show me roughly what you're looking for, the point. So I'm looking for this x-intercept here, roughly. Enter, and it will calculate the x-intercept for me. Oh, it's a simple x-intercept, 2, 0. Okay, now what about finding the y-intercept? Where does this graph hit the y-axis? That you can do by second calc and do value, number 1. Number 1 tells you you can put in any x value you want, and it'll tell you the y value. At the y-intercept, the x value is 0, so I'm going to put 0 in there, enter, and it tells me 0, -8. So that point is 0, -8. So I have enough to draw that sketch, and here's what the sketch can look like. Right here, we have 0, -8, y-intercept. We found the x-intercept to be 2, 0, and we have our graph. Try the same thing with B. See if you can sketch that one accurately. What are the x-intercepts and the y-intercept of that one? Okay, in B, when you graphed it, you may have to adjust your window a little bit, because look how low these y values go. So maybe you adjusted your y values to have a y min of -50 like this. If you didn't do the adjustments, do them now. Look at the window it gives here and adjust your window like that. Do a y min of -50, y max 10, do an x min of -4, and an x max of 8. And you should see this exact thing on your calculator. So there's our cubic. It has one x-intercept, you were asked to find that one, and it has one y-intercept, you were asked to find that one. So I hope you found those all right. Okay, another question. Are all cubic relations functions? And do all cubic functions have inverse functions? Let's think about what functions mean again. So we're going to look at Desmos for this as well. So I'm back in Desmos here. We have a cubic function here. And I'm also going to graph a vertical line. Remember, the vertical line test tells us that something is a function, because if we draw a vertical line and it hits once, it means that for every x value there's only one y value. And remember, that's the definition of a function. Every input produces only one output. So I'm going to slide that vertical line across. Does the vertical line ever hit twice? No, never. that means this cubic is a function because every x value produces only one y value. Now let's change the shape of it a little bit and see what happens. Let's see. Oh no, let's look at another one. So here's another cubic. I'm going to close the first one, this one. Now let's check if this one's a function. Does the vertical line only hit once everywhere? Yes, it does. So that means this cubic is also a function. Now something you should know is that every cubic will be a function. You'll never have a situation where the vertical line will hit twice. There will always only be one output for each input. So now let's go back to this one. The second question was, will the inverse of this be a function? And you may remember we did something called the horizontal line test. So here's a horizontal line now. If the horizontal line hits twice, then this thing will have, if the horizontal line only hits once, then this thing will have an inverse, which is also a function. Because remember in an inverse, we swapped the x and y values. And if we swap them, then the vertical line test became the horizontal line test. So here we go. It only hits once always. So this one will definitely have a inverse that is a function. Let's look at the second one. So here's another cubic, one of the ones that has max and min points. And let's run the horizontal line across that. Does it ever hit twice? Yes, it does. Look at that. Here it actually hits 3 times. That means for that output, there are 3 different inputs, 3 different x values that can produce that same y value. And that means if you inverse this, you would have the situation where one input produces 3 outputs, and that would make the inverse not a function. So really important to see that. Sometimes cubics will have inverse functions, sometimes they will not. Let's look at that some more in our presentation. So here is the first one graphed. Okay, so x cubed minus 2 graphed. Looking at that graph, does this one have the max or min points, or is it the kind of cubic that has no max or min? Well, it's the kind that has no max or min, right? There's no like hill and valley. It just continues upwards. So this kind will always have an inverse function. And if you remember to find an inverse function, we can swap the x and y values. So let's find the inverse of this one. We begin with the original, then we find the inverse. We've done this process before, but let's take a look again. We swap the x and y values, so this became x, this became y, and now we solve again for y. So I'm going to add 2 to the x, now I have y cubed equals that. Now I'll take a cube root to get rid of this cube here, so cube root gets rid of that, and then we have a cube root here. So this will be the inverse function of this one. If you put that on your calculator, let's try it, enter that equation on your calculator, and you should get this graph here, the green one. So now you have the original and the inverse graphed, and remember the inverse and the original always reflect over the line y equals x. So here's the line y equals x, and you can see it's a perfect reflection. So we have the original one and we have the new one, and both are functions, because again, we know when we have a cubic that does not have the max or min peaks, then it will have an inverse that's also a function. Because the blue one passed the horizontal line test. The horizontal line always hits it only once. And now, on the green one, which is the inverse, the vertical line will only hit once. Because the vertical line on this one is the same as the horizontal line on this one. So all these important functions ideas, I hope that's all making sense. Let's look at the next one to compare and see how it's different. So this one, graph this on your calculator. All right, here's what that graph looks like. Again, it's one of the ones that it does not have the multiple peaks, like it doesn't have a max point and a min point. So we know right away it passes horizontal line test, so its inverse will also be a function. Let's take a look. Let's find the inverse. Here's the original. Inverse, swap the x and y like this. Then we're going to subtract 5 over here. Then we're going to divide by 4 to get this. Then again, we have a cube, so we take a cube root to do that. Cube root. And we have this entire function. Oh, and cube root, and then subtract 1 at the end. So here's a 1 that's been subtracted at the end. So please follow that, those steps carefully to get the inverse. If you graph that on your calculator or Desmos, you will see this graph right here, the purple. And we can see the inverse is a function also. The inverse passes the vertical line test. For every input, there's only one output. And we know the inverse passes vertical line test because the original one passed the horizontal line test. If the horizontal line only hits once, then the vertical line on the inverse will only hit once every time as well. So it is a function. We can see perfect symmetry over y equals x. Let's finish by going back to Desmos and reminding ourselves. This one will not have an inverse function because the horizontal line hits many times. So if you create the inverse graph, the vertical line would hit many times. All right, just keep that key idea solid.